Hey, my name is Mark Schvetz, and I'm a developer at Chariot Solutions. This is the last talk of the day, and we're finishing strong with a really meaty topic. Some of you may have heard or even have used Cassandra to store large data sets across multiple servers. Jonathan Ellis's company, DataStax, takes Cassandra to the next level. In this talk, we're going to find out the next cool things coming out of the massive distributed storage. Take it away, Jonathan.
Thanks, Mark. My background is in Cassandra, and that's like my passion, but this talk isn't like, it's not a Cassandra talk. It's a talk about what I see happening in the industry across, basically all the databases out there, what I expect to see happening in the next approximately 5 years. So I've got a URL here, and for those of you on Slack, I'll put it in room A as well. And what this is it's if for those of you who are old like me, you'll remember something called Google Moderator that back in the day let you ask questions and vote them up. And Google killed it, like they kill a lot of their stuff. But this is basically the same idea. You can ask questions during the talk. You can vote on other questions, and at the end, I'll click over to that and and answer the questions at that time. So I won't be doing questions during the talk, and I won't even be watching Slack. I'm going to exit Slack now because the Slack notifications can be distracting. But I will go to this, and I'll post the URL one more time at the end, but I'll take the questions at the end. So I have 5 areas that I want to make some predictions in, and so in 2025 maybe we'll come back and see how I did. But across machine learning, across cloud, open source and hardware are related but distinct from cloud, and then finally in the graph database space are where I'm going to make some predictions. And the lens, those of you who attended my talk last year, I had almost the exact same slide. I want to share the lens that I'm looking at the landscape through. So I divide the database world into kind of 2 axes. Are we targeting operational workloads like running my application day to day, or am I targeting analytical workloads more particularly? And then the other axis is it a scale up architecture or a scale out? I want to distribute across multiple machines. And so I spend most of my time in the upper right-hand corner where Cassandra lives. I have a reasonably good understanding of the upper left as well and the lower right. So those are kind of the adjacent spaces, and much less of the lower left. So if you hear me say something and you're like, wow, that doesn't make any sense at all, maybe if you kind of box it into that upper right, that might help it make a little more sense. I'm not always going to call that out explicitly, that's the only thing I'm talking about, but sometimes that's implicit in my worldview. So the first area is what is machine learning going to do to the database space? The first thing is that there are already companies out there that are going to try to sell you, a database for machine learning. Like our database has machine learning built into it. Like you don't want that. You don't need it. There's a couple reasons for that. The first reason is that machine learning is, of course, matrix algebra. Like it's all you need from the database is be able to store and retrieve vectors, and basically every database in the world can do that. And depending on the volume of your machine learning data set, like some databases are going to be better or worse choices than others. But for the most part, like that becomes a question of, can my database scale, not can my database support a machine learning application on top? And so the other reason is that what I'm trying to get across with this slide is that there's all kinds of projects dealing with machine learning that are specializing in this aspect or that aspect. So it's the wrong time to be trying to pick a single approach and bake that into your database and say, this is how I'm going to do machine learning. You want the flexibility that comes from separating the machine learning part away from the data storage and retrieval part. Yeah, so since I'm coming from the Cassandra world, Cassandra is actually really good at the kind of storage and retrieval of vectors that you do with machine learning. Uber built a machine learning pipeline called Michelangelo that's built on Cassandra, for example, but like it's pretty straightforward from the database side. What I think is more interesting is what happens when we apply machine learning to operating databases, and what can we do with that maybe we couldn't do before. So the first area where this seems like an obviously good idea is tuning your database for a specific workload. So this is a bar chart where the y-axis is how many knobs are there for me to tune in my configuration file or data dictionary for my database. So Cassandra is clocking in at around 170, PostgreSQL around 300, and MySQL is pushing close to 600. And somebody told me the other day that Oracle is up to over 900, which is kind of insane. But I mean, even at the lower end of the spectrum, even 170 with Cassandra, that's more than humans can reasonably be expected to deal with in a sane and intelligent fashion. So, if you look at the date on this tweet, this was I was about 6 months into DataStax at that point, and about 2 years into Cassandra. And I said that, if you're building a database and you add a configuration option, like that's like a crime against your user base. And yet, I personally created a bunch of these configuration options because there isn't really a better alternative. So for example, in Cassandra, the row cache is something that's existed since Cassandra 0.3, which was the first release that we published as part of the Apache incubator. And what it does is it says, like, if you're reading rows from a partition in the database, you'll probably read those rows again, and it might make sense to cache those in memory rather than deserialize them from disk, which, since Cassandra is a log structured storage engine, can require reading from multiple data files and reconciling the different versions of the rows. And so we have a configuration parameter called row cache size in megabytes. And this is a good example of a place where it would be really difficult for Cassandra to figure out what that should be without a human telling it what's appropriate for this workload, because it's going to vary from workload to workload, whether whether a larger value is better than a smaller value, or even whether enabling it at all is appropriate. And so the state of the art is, as an expert, you want to get your expert's going to make an educated guess, but they're still going to have to try it out to see if it actually helps, because it's a complex system. And so what you end up with is there's a half a dozen, maybe a dozen settings like this, that if you hire a Cassandra expert to tune your database, they'll come in, and I believe the situation is substantially the same for the other databases I mentioned. They're going to come in and they're going to go to that, those dozen high impact settings, and they'll test out some different options there. But the rest of the 100+ options, they're probably not going to bother with, because their experience shows that there's diminishing returns. And if you're paying them hundreds of dollars an hour to do these tuning for them, then you're probably not going to be willing to do that to get an extra 0.001% performance increase. So Andy Pavlo at CMU is probably the world's leading expert at doing this in the research space. He's created an open source project called OtterTune that, and basically it says, computers are really good at doing a couple things better than humans, and one of them is doing boring things over and over in an automated fashion. And so what OtterTune will do is it will explore not just those top 10 most important configuration dials, but it will keep on exploring that in the background and trying different settings on the rest of those long tail of options past the point that a human would be able to pay attention. And so you can, what they did in their study is they actually pitted OtterTune against a human expert, I believe it was for PostgreSQL, and said, can we actually beat the human? And the interesting thing here is that they did beat the human, except that the human cheated from OtterTune's perspective. And he said, and he realized that because of the way the application worked, there were certain options that that were safe to enable that wouldn't be safe if the application were doing something else. And OtterTune had no way of knowing that, but the human was able to take advantage of that. So there is still a space for humans in our machine overload ruled future, but the machines are catching up. But the other thing that OtterTune does that has to do with the topic of this section, which was machine learning, is that it keeps a database of the different workloads that it has seen and what options it generated to best improve performance for those workloads. And so when it sees a new workload, it can interpolate from that to the other workloads it's seen and say, here's a good starting point for this workload I haven't seen before. And I'll start from there instead of starting from 0 or starting from a default configuration. So really cool project, and I think that this is the future. So this is going to be not just for the database level configuration, but it can apply to operating system tuning. It can apply to for Java applications. It can apply to the JVM, and it can start going past that and saying, well, I want to predict failures before they happen. I want to predict disk failures, which is relevant. If I'm running a database, the disk failure is going to slow me down at best, and depending on my tolerance for failure, it might actually take down my service. So I want to predict those in advance, and I want to also predict load spikes. So that's another characteristic of my application that tends to be something that I can predict the future from what I've seen in the past. So there's a lot that we can do to make databases better with machine learning. The other two the two that I've got an asterisk next to here, these become much more powerful when I start getting into a world where my database is automatable with something like Kubernetes or a native cloud service. So I'm going to talk about that in the cloud section coming up. But the bottom line is that all of these self-managing features I'm predicting are going to be common within the next 5 years. And so the graphic here is self-driving cars. We thought it was hard, and then we thought it was easy, and now we think it's hard again. So I believe that self-driving databases are easier and more tractable than self-driving cars. So that brings us to talking about databases in the cloud and what's going to happen there. I think there's two kinds of cloud databases, and it's important to distinguish between those. So on the one hand, you have what in general I would call a managed database, where And this would be like Amazon's RDS is a good example, where it's SQL based. You get full, everything that comes with, all the flexibility that you would expect from MySQL or PostgreSQL. But that means in exchange for that, you're also getting that bottom bullet point of you're not completely getting away from the requirement of doing some administration work on that database. On the other hand, if we have what I'm going to call a native cloud service, then they're very focused on providing a zero administration experience. And also the third bullet point being infinitely scalable. And in exchange for those two, they're going to give up some of the first two around being full featured. And we're going to say, we're going to give you a partitioned architecture. That means that your queries are going to need to be simple and fast. So you're not going to have 5-way joins with subqueries and so forth. Like, it doesn't handle that. You've basically got look up a row by a primary key, probably some version of look up a row by an index. And that's probably about it. And if you're going to support joins, you're going to pay a performance penalty to get that. And you're going to be upfront about that in your SLA. My prediction is that the native category is going to grow faster because in the applications that people are building today, the second two bullets are more important than the first two. And that's why the operators will be willing to pay a premium to get those two properties of being infinitely scalable for, there's going to be some fine print next to infinitely, but, effectively, you're going to be able to scale your database by throwing more money at your vendor. It also means that you get a faster time to market from that fourth bullet of zero administration, because your developers don't need to understand the database to the degree that they would in a traditional environment. They can treat it as a black box of, if I make this query, then I get back these results, and my SLA is that I get it back within N number of milliseconds. And for the most part, that's the end of how deeply I have to think about it. There's another interesting part about native services, which is that a service provider should be able to offer it to you as a consumer cheaper than the traditional alternative, because you can do CPU arbitrage. And what I mean by that is, I can do maintenance operations, like in the Cassandra case, I'm going to be doing anti-entropy repair, and I'm going to be doing compaction, and I can do those in non-peak instances. So I can send that to spot instances that I spin up, that I do the compaction on, and then I retire once I'm done with that operation. And so I want to save my full price VM hours for serving user requests. In the PostgreSQL world, the equivalent is doing vacuum. I want to be doing vacuum with cheaper CPU than serving the user's inserts and selects. So an interesting question, at least for me, is what query language are we going to see become the lingua franca of these cloud native databases? So I've already posited that it's not going to be SQL kind of by definition, because that pulls you out of that simple and fast and scalable category. So there's a couple candidates. I would say that it was more common to hope for and suggest this a few years ago than it is today. I think that by and large, there's a recognition that REST is both not expressive enough and also not performant enough to be a general purpose database API. There was what looks like a really interesting GraphQL talk in the last hour that I missed because I was watching a different talk, and I'm going to come back and check the recording. But I do think there's potential for GraphQL to become the lingua franca here, and it addresses the pain points that we had with REST to a significant degree. Another thing that I'm going to put forward as not as a prediction, but as an interesting possibility is the Cassandra query language is starting to look like it's becoming kind of a de facto standard where you have, besides Cassandra, you have Microsoft Azure Cosmos DB supports Cassandra query language. Amazon's DynamoDB supports Cassandra query language. Startups are supporting it. So Yugabyte is a database startup that supports Cassandra query language. So there's some evidence that this might be a sufficiently expressive language for NoSQL databases in the cloud. Some of the things that I think are going to be table stakes for this native category is first, there needs to be a free tier. And I'm going to come back to why I think this is important, but I'm just going to throw it out as a principle for now, and I'll defend it in just a minute. But the other thing is that there's a lot of interest in hybrid cloud, and to get there, basically the market is insisting that you support Kubernetes as part of that strategy for hybrid cloud. And I was not on the Kubernetes bandwagon as recently as maybe 18 months ago. There's a lot of complexity, and it started out in the space of I want to manage things that are stateless, which is very much the opposite of databases, so it wasn't a very good fit. But at this point, Kubernetes has won its category so thoroughly that you can just accept it. It's not worth arguing about anymore. And by the way, they have added support for stateful services to the point where you can build database support on top of it. So I believe that both of these are going to be, or they're already table stakes for the category. Meanwhile, so when the terms hybrid cloud and multi-cloud are overloaded, I'm going to use the terms to mean hybrid cloud is talking about I've got hardware that I manage or that I pay someone to manage, and I'm using a public cloud as well. And if I'm going to talk about, well, I want to talk about using multiple public clouds, then I'm going to say multi-cloud instead. And the interesting thing here is that Kubernetes everywhere doesn't actually get you to multi-cloud, primarily because we're still dealing with very different fine-grained access control labels across the cloud providers. And having a Kubernetes deployment that works across multiple cloud vendors basically still requires per cloud permissions or overly broad permission assignment. And so if I'm going to make a prediction here, it's that somebody's going to see this problem and start the work of fixing it, because it definitely needs to be fixed. So I have two shameless plugs in my talk. This is the first one. DataStax has built a Cassandra as a service in the native cloud database space. It's called Astra. And the easiest way to find that is to just Google DataStax Astra. It's been in beta since October. And definitely the easiest, if you've never tried Cassandra, this is definitely the easiest way to get started and see what that's about. My third category that I want to make a prediction in is open source, and this is something that I've been I've been very involved with open source Cassandra for 10 years, and involved with other open source projects before that. So I think that there's kind of three really broad eras of open source, and so we started with Richard Stallman. Well, it's not exactly accurate to say it started with Richard Stallman, because people were doing effectively open source in early research environments without calling it that. But the first person to give a name to it was Richard Stallman in the 1980s. And his position was that selling software is actually unethical. And he's talking about free as in freedom. And as a user of software, if you don't have the freedom to make changes, then you're in a form of bondage, and that's bad. And that's bad for you, and it's unethical on this part of people who sold that to you. So his standpoint was, if you're a vendor and you want to be in the software business, you should support yourself selling services, but the actual software should be free with a capital F, which to Richard Stallman meant that it should be under the GPL license. And then in the 90s, I think it's fair to say that this was catalyzed by Linux and Red Hat, and the open source initiative that kind of formed around that said that selling software is fine, but it's just not as powerful because closed source is inherently less easy to adopt and doesn't have the virtuous cycles that you can build with open source. And so yeah, your product should be open source, not because it's unethical to do otherwise, but because it's in your own best interest as a vendor. And you should, if you're building a business, you should do that as products built around an open source core. And then that lasted until fairly recently, and I think we've recognized as an industry that we've entered a third age where, and I'm using some loaded language because I'm part of this, I'm living this. Anything you open source will be strip mined by the cloud vendors, and so because of that, there's a third category of how you can build a company, which is by supporting yourself with complementary products and services to that. And I said cloud vendors, and then I also said in parentheses some of the cloud vendors, and there's like it's not a one size fits all brush that I want to paint this with. And even within the different cloud vendors, like these are all really large companies with really large cloud divisions. And so, everything I'm saying here is like, you're going to be able to find exceptions to it. But super broadly speaking, Amazon says, we're going to white label open source as a service. Microsoft's tendency is to say, let's copy their APIs, but we're going to build our own service, not based on that code. And Google is taking a much more partnership-oriented approach of, let's partner with the open source vendor and build a service together. So from my perspective, the Google approach is a lot healthier, and I'm hoping to see that make traction with the others. Meanwhile, what you see a lot of the infrastructure companies doing that are built on open source is reacting to this dynamic of the cloud vendors competing with them with their own projects, is to change the license. And so Confluent, which works on Apache Kafka, the Kafka core itself is still Apache licensed, but Confluent changed its extensions from Apache to a new license that they call the Confluent Community License. Similarly, Redis Labs has created a Redis source available license. Elastic has created an Elastic license. MongoDB is kind of the exception here because they've moved everything. So not just the extensions, but they've moved everything from AGPL to server-side public license. And I think that that's a relevant thing for them to do today, but I don't think that it changes the dynamics long term. And so what I think you're going to see is that companies are going to create as a service offerings, and that's going to become the adoption vector more than open source. Because if there are, I don't know how many millions of people using Amazon services, and really they don't care that none of those services are open source. What they care about is, I'm reasonably confident that the price is going to stay low, and it's super easy to get started. So like I think a lot of people, myself included, misunderstood that open source as being like people liked it because they had the source. But really the important part about open source was or not the only important, but one of the most important things about open source is that there's no like click-through agreements. There's no filling in a form and having a salesman call you. You could go grab it, download it, and use it, and you were good to go. So it's easy to adopt, and it's inexpensive. And building software as a service makes that adoption part even lower. And that's the part that's even more important than the price tag. So some examples that you see today: Snowflake in the analytical database space, Tableau data visualization, Databricks, also loosely speaking data analytics space. I think these guys are nailing it. Coincidentally, all of them are doing very, very well in the market. None of them are open source, but all of them have a really easy to use service that you can get started with for free. As a corollary, I do believe that we're going to see less open source overall, because the incentive for companies to give away their source have been reduced because of this dynamic. Like, we can talk about whether that's a bad thing, but I think that's the world we're living in. And of course, the hype matters, where there were companies 10 years ago that were using an open source model because that was the cool thing to do, and I think that motivation will be less relevant. So on the hardware side, this is the shortest section. I think we're going to see again the dynamics of the cloud driving what goes on here. That even if I'm so in DataStax's world, close to 100% of our customers have some footprint of hardware that they manage themselves, and roughly 2/3 also have a foot in the cloud. And so what's going to be driving what they care about in terms of hardware is the cloud, because that's where there are constraints. So you can't just deploy any hardware you want into the cloud. You're limited based on what your cloud vendor is offering. And so because of that, my prediction is that specialized compute will not be relevant. And I have a asterisk next to that, because again, coming back to that second slide I showed where I said, here's what I'm talking about when I'm talking about databases. I'm talking about scale out, and I'm talking about operational workloads. So I think it's very clear that on the analytical side, everybody, GPU computing is mainstream, like that no question that's relevant. But on the other hand, you could say that's not actually specialized silicon at this point. And so, either way, my point stands that, if you're looking at the cool things you can do with FPGAs or custom ASICs, like, that's really cool and super interesting, and I'd love to nerd out about that, but I don't think it's going to be relevant in the market. So and I want to specifically say that I love Intel's Optane storage technology, but I think this falls firmly into the category of it's not going to matter. So for those of you who don't pay quite as much attention to this space, Intel uses Optane to mean two different things. One is as a SSD that you plug in, and the other is as a DIMM form factor. So this is a picture of an Optane DIMM, and Intel's pitch is that it's persistent memory with within a factor of 10 of access time to DRAM, but it's persistent, and you can use that as part of your database. And what I believe is that SSD access times are low enough that it's not a bottleneck for people today. And the right thing to optimize for is density. That's going to be what drives your cost rather than latency, which is what Optane optimizes for. So, and there's definitely edge cases where I can think of some DataStax customers who do care about that latency and use Optane for that, but it's definitely a minority. So the last and possibly most controversial prediction I have is that Graph is a feature and not a database. So, and here again, there's different things people think of when they think of graph databases. One is RDF triple stores, and then others what's called property graphs. And I'm talking about property graphs for the most part, but this would also apply to the triple stores. Graph databases are good at a bunch of things that relational databases are not good at, especially recursive queries. And conversely, there is stuff that graph databases are not good at. And typically it's like the inverse, that anything that looks like a table and that you can easily visualize as a table, graph databases are probably not going to be good at that. And so the first question people ask naturally is, well, can we just add graph features to non-graph databases? And then we kind of get the best of both worlds. And you can, and in fact, you can do it, you can brute force it trivially. And that's basically what Oracle has done. But the B-tree storage engines that typical relational database are built on are actually a really bad fit for graph data that needs to be performant, because you're doing, a graph update is going to touch hundreds or even thousands of leaves on a B tree, and that's just going to kill your performance. And log structured storage engines, on the other hand, because they're inherently storing data adjacently on disk, it actually lets you build an adjacency list based graph engine fairly easily and in a performant manner. So this fragment of code here is from a book that I'm going to show in a couple slides, where they basically go into detail of, here's how you would represent this graph as an adjacency list, and specifically what that would look like for Cassandra. So the book's called The Practitioner's Guide to Graph Data. So this is by Denise Gosnell and Matthias Brechler. Matthias started a database company, a graph database company called Aurelius, one of the earlier entries in the field. DataStax bought his company in I want to say 2016, it might've been 2015. And so he's been thinking a lot about, how do we marry the graph and the tabular worlds? And Denise has been working on the services side at DataStax, helping customers actually build graph-based applications. And so the book basically represents, how do I marry a graph technology with tabular data, because real world applications more often than not require both. So this is my second shameless plug, is that we've built a graph database into our enterprise Cassandra called DataStax Graph. And here's what this looks like at the DDL layer, where on the left you have creating a table, and then at the bottom in bold we have and vertex label, person label. So that's saying I want to be able to access this table normally as a series of rows, but I also want it to be able to represent a graph, a set of graph vertices. And then on the right, we've got a slightly more complex example saying that, and again at the bottom in bold, where this table represents graph edges between person vertices and software vertices. And so we've been able to bring those two worlds together. And you can try that out from downloads.datastax.com. What you want is DataStax Enterprise 6.8, and then you're off to the races. So I'm going to come back now to my questions thing, and I'll see if any of those have come in. I hope that this is still working. And we have 0 questions. So it's possible that you all are just phenomenally bad at following directions. So I'll come into Slack, see if there's any questions in Slack.
There are not. But you have 114 people here. I can't believe there are no questions.
All right. Well, thanks for helping me finish on time, everyone.
Oh, something is coming.
So a question about any speculation about new open source business models. I mean, I hate to say that I don't have a good answer, but I don't have a good answer. So the classic answer, as I had on my slide, is around, let's do products that integrate with this open source thing that I'm running as a service. But at that point, if I'm starting a new company, why not just run the service and not bother with the open source part? Like that's the dynamic that I have a hard time getting away from. Do we have the ability to let participants use the microphone here?
Yes. Which one? You want Martin to talk? I can actually do that.
That could be an option, but we've got things coming in here.
Okay.
When Cassandra adds features of a graph database, or Solr adds features of a graph database, or Postgres adds JSON or full text support, is that the right answer? That's basically what I'm saying, is that to the degree that graph technologies solve interesting problems for businesses, that those are going to get integrated into PostgreSQL or Cassandra or Elasticsearch. Yeah. Do we want one-size-fits-all databases, or are we okay with best of breed? So in the 5-6 years ago, it was part of the NoSQL hype wave was, hey, let's do polyglot persistence, and let's use the best tool for every job. And but the motivation or the drive for each of those products is to try to tackle more use cases over time. And so, in 2010 and in 2020 as well, for that matter, Cassandra, there's a class of problems that Cassandra solves 10 times better than MySQL. And so that's why people use Cassandra. But if you're going to say, I've got a database and it solves this problem 20% better than Cassandra or 20% better than MySQL, then I'm going to look at that and I'm probably going to say, that's not enough of an improvement to be worth standing up a separate piece of infrastructure for that specific thing that you're doing 20% better. So I think the pendulum is swinging towards let's do more with fewer tools, because the tools themselves are getting better at doing more. More detail about how the adjacency list examples work under the hood. Basically, the idea is that you would have a Cassandra partition per vertex. And in that partition, the rows in that partition are going to be the edges that you have to other vertices. And so then it's just a Cassandra primary key lookup or a partition key lookup to get the rows from that partition to say that, here are the pieces of software that Jonathan has starred on GitHub.
We have a question up top. How can I recognize relational data that is better stored in a GraphDB?
Like my basic rule of thumb is, if you want to do a recursive query, then that's a really good candidate for a graph database.
Ooh. Is DataStax involved in any COVID-19 analysis activities that you can talk about?
We actually open sourced a proof of concept for tracking connections between patients with COVID-19. But there's 500 people who have created proof of concepts. So I'm not sure if that's going to go anywhere.
Oh, there's more on the bottom.
So there's a whole problem in graph databases about, or rather about distributed graph databases, about how do you partition your graph so that the most common queries can be satisfied from a single machine and not have to hop from machine to machine. And it's provably impossible to have a partitioning that's optimal for every query. And so then there's a whole lot of PhD theses about, here's how we would optimize that placement for this specific class of problem, but it's basically a pick your poison kind of situation. So in other words, there is no silver bullet to get around that problem completely.
All right, I think this is it. Jonathan.
Well, thank you everyone for joining us for the last talk. Appreciate it.
Thank you guys for coming to the conference. This is the last talk of the day. Thank you, Jonathan, for speaking. We were so happy that we could put it on. Yeah, there's a you typed it into Slack, sir, or madam. So thank you so much for taking the conference online. It was our pleasure to host it, and it turned out pretty great.
Thanks, Mark. Thanks, everyone. Have a good one.
See you all next year.